Hello and welcome to my presentation on a collaborative approach to specify sensor models. Virtual testing plays a major role in the development of automated driving functions, and models of environment perception sensors are a big part of that. Currently, a lot of expert knowledge goes into specifying the development of said models. Experts have to go through hundreds of research publications to evaluate what effects on sensor data are relevant and should be modeled. And this is really hard to do, if not impossible, for one test engineer. So how can we improve that? And how can we make the specification process easier and at the same time increase traceability for the decision-making process? We propose the following method. First, known sensor effects on sensor data need to be collected from the literature. Then, cause and effect chains need to be derived from these known effects with the help of functional decomposition. Third, these cause and effect chains need to be analyzed according to their relevance for a specific system under test. And from that, a functional specification for a sensor model can be derived. Before we dig a little bit deeper into the method, let's quickly talk about the terms we're using. Let's consider an ego vehicle with a front-facing sensor, can be a radar, LiDAR camera, and we have an object of interest we call target. In this simple example, we also have another object, in this case a wall, that is occluding the direct field of view from the sensor to this object. This sensor we consider to have a data processing unit that has an object tracking or object identification, and it will output an object list. So what will happen in this scenario? Of course, this target will not be visible. So in a ground truth, it is there, but it's not detected, so we consider it a false negative object. And every observable effect at the output of a sensor system we call phenomenon. And this phenomenon is caused by the occlusion that happens during the signal propagation in the environment. And every deviation from the originally existing information about the environment in the signal data we call an effect. And effects can occur in different parts of the signal processing of a sensor. So it can be already during emission, can be during signal propagation, in the reception, and so on. And for every effect, there's one or multiple causes. And as a cause, we define every condition leading to a deviation in the information. So in this case, a cause would be the wall position, but also the wall material. If this wall would be made out of glass and we would have an optical sensor, this occlusion effect would not occur. And this also comes down to causes from the system itself. So in this case, the emitter wavelength plays a role because different wavelengths interact with materials differently. So this is also a cause. And we can see a difference between these two kinds of causes. So we differentiate between system-independent causes, like the wall position or material that only rely on the environment itself, and specific design parameter of the sensor system we're using. So the emitter wavelengths is a parameter that's specifically designed by the engineering team of that sensor. And then we can sort these causes, effects, and phenomena into different parts of the signal processing of the sensor. We get these parts from functional decomposition. And in this simple example, we only have an emission block, we have a signal propagation block, and we have object identification. We can sort that into these blocks. As a next step, we can connect causes and effects. So we know these are the causes for this effect of occlusion within the signal propagation. So we can connect these. And also this effect is the reason for the overall phenomenon at the end. So we can also draw a connection here. And then for every connection, we can link scientific literature. So conference publications, journal papers, books, and so on. So we can link this literature to prove, first of all, that the effects really exist, and then again that these are the causes for this effect. And as you can imagine from the simple example, this will become very complex. We're a little bit more advanced example, but still quite limited. And we really stress that this cannot be done by a single person for the complete state-of-the-art on sensor effects that are out there. So we stress that this is a collaborative approach, and we call it perception sensor collaborative effect and cause tree, in short, PerCollECT. But this is a mere collection of the state-of-the-art, an organization of the state-of-the-art. So this alone doesn't specify a sensor model. So we need to go further. And we need to analyze individual cause and effect chains. In this example, we start at the top from our false negative object, and we go all the way down through the decomposition layers and all the underlying effects down to the causes at the end. And we can extract these cause and effect chains automatically from PerCollECT and put it into a table format. So we have our phenomenon, we have the effect chain, and we have the underlying causes. And from this, we can consult experts. And this method here is loosely based on the failure mode and effects analysis method, where also experts are consulted. So here we propose to first consult a sensor expert, so an expert on the specific sensor system that's used. And this expert will evaluate the likelihood of the occurrence of this individual cause and effect chain within a given operational design domain. And the expert will give a score between 1 and 10, and this is the exact same scoring scale we have in the FMEA for occurrence. And the expert will also give a rationale, so reason for his or her evaluation here. Then we will consult a second expert. This is not a sensor expert, but an expert on the specific system under test that will be tested in this virtual environment. Also score between 1 and 10, but here on the impact of the system under test. So how would this phenomenon, if it occurs, impact the specific system under test? Again, with a reason and a rationale for this evaluation. And then by building the sum of these two scores, we will get an overall score. And we deliberately take the sum and not the product to stress individual high ratings in these two categories. And this method, this table consulting the experts, we call cause effect and phenomenon relevance analysis, in short, CPRA. Now, we didn't want this to be a theoretical consideration in some research paper. We really want to bring it to life. And that's why we implemented an open source platform on GitHub where everyone can collaborate. So feel free to check that out. And we implemented individual repositories for all the major sensor technologies. So we have LiDAR, camera, radar, and ultrasonic. And within these repositories, we have, first of all, a backend, and that is XML based. So we have an XML file for every sensor effect containing a description of the effect, what functional decomposition block it belongs to, all the connections, the links to scientific literature, and so on. And then we also have a front end to visualize the PerCollECT tree. And let me quickly show you how that looks. So we have the tree visualization, and you can zoom in and browse through that. You can follow down these cause and effect chains all the way down to the underlying causes. You can also select an individual effect and highlight what the causes are, and also what the effect then on the top causes as a different effect. You can also click on this little information icon, and you will get a more detailed description on the effect. You will get the reference to the scientific literature, also with a little description for it. And as you can imagine, this tree will get more and more complex as more people collaborate. So we implemented a search bar. So on the left top here, you can search, for example, you're interested in noise. So you search for noise, select an effect, and then only a partial tree will appear, going down from that effect, and you can see the underlying effects and the causes for that effect of interest. So in conclusion, we built a collaborative open source tool to collect and organize cause and effect chains, and we call it PerCollECT. Secondly, we introduced a method to analyze the relevance of cause and effect chains for the sensor model specification, and we call it Zebra. And as an outlook, Zebra is only one application example for PerCollECT. PerCollECT can be used for a variety of different applications. For example, you can use it for scenario design to consider sensor effects early on in the virtual validation process. And you can also get away from the virtual world and use PerCollECT to derive effect mitigation methods for real-world systems. And of course, the more people collaborate on PerCollECT, the more powerful this tool will get. And then as another outlook, we can imagine not only to link literature as a proof for individual effects, but also real-world measurements. So we can think of a database of measurements that's linked to PerCollECT, and you can directly get measurements that really demonstrate that this effect really exists in the real world, and demonstrating its relevance. And lastly, OEMs can potentially use this tool to derive a systematic, standardized, and semi-automated process for the overall system homologation. PerCollECT and Zebra were developed in the two German research projects, ZLevel and VVM. And as a matter of fact, they are, we're starting to really apply this method in the VVM project to specify a LiDAR sensor model. And from the specification, from the requirements that we derive from this method, we will develop an overall sensor model validation scheme in this VVM project. Yeah, this is the conclusion of my presentation. And thank you for your attention, and have a nice day.